Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into one of the most iconic system design problems in the world, designing WhatsApp. With over 2 billion users sending more than 100 billion messages every day, WhatsApp is a masterclass in real-time, secure, and globally distributed messaging. We'll cover how text, media, groups, status, voice and video calls, presence, last seen, and multi-device sync all work together at massive scale. Whether you're preparing for a senior engineering interview or building real-time communication infrastructure, this one is for you. Let's get into it. Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into one of the most iconic system design problems in the world, designing WhatsApp. With over 2 billion users sending more than 100 billion messages every single day, WhatsApp is a masterclass in building a real-time, secure, and globally distributed messaging system. If you have ever wondered how a chat app delivers text, images, videos, voice messages, and calls with end-to-end encryption, while keeping users' online status, last seen, message sync, and groups working at massive scale, this video is for you. We'll walk through the functional requirements, non-functional requirements, system architecture, end-to-end user journey, core models, low-level design, and the trade-offs that come up in a senior system design interview. Whether you are preparing for a FAANG interview or building real-time communication infrastructure, let's get into it. Here is the core problem. 2 billion users expect instant, reliable, and private messaging across every device in every network condition. They expect that when they hit send, the message arrives in milliseconds, whether the recipient is online or offline. They expect that a photo or video sent in a group of thousands of members is delivered to everyone quickly. They expect that voice and video calls connect reliably, even across continents. They expect that their status updates are visible to the right people. And they expect that no one, not even WhatsApp itself, can read their private messages. That is the end-to-end encryption promise. Behind the scenes, this requires handling enormous message volume, storing media at low cost, synchronizing messages across phones and desktops, managing presence and last seen, and scaling chat, group, and call infrastructure worldwide. The design challenge is to keep latency low, availability high, storage efficient, and security uncompromising, all at the same time. Let's walk through the functional requirements. First, one-to-one chat must support sending and receiving text, emojis, images, videos, voice notes, documents, and location messages. Second, group chat must support creating groups, adding or removing members, and sending messages to up to thousands of members efficiently. Third, status and stories must allow users to post ephemeral photos, videos, and text visible to their contacts for 24 hours. Fourth, voice and video calling must support peer-to-peer or relayed calls with low latency and good quality. Fifth, presence and last seen must show whether a user is online, when they were last active, and support privacy settings like hiding that information. Sixth, message sync and multi-device support must allow the same account to work across a phone, desktop, and web without losing history. Seventh, end-to-end encryption must protect messages, calls, and status media, so that only the sender and receiver can access the content. These 7 capabilities define the WhatsApp experience. Now the non-functional requirements. The system must deliver messages with extremely low latency, typically well under 1 second for online users, and within seconds for offline users after they reconnect. The system must be highly available, because messaging is a utility that people rely on for personal and business communication. It must scale horizontally to support billions of active users and tens of millions of concurrent connections. Security and privacy are non-negotiable. End-to-end encryption must be the default for chats, calls, and backups. The system must be reliable, with message delivery guarantees, ordering guarantees, and deduplication. It must be efficient with storage, media, and bandwidth, because users are on mobile networks and limited data plans. And the system must handle global distribution, with users, data centers, and chat servers spread across the world. Here is the high-level system architecture. On the left, Mobile and desktop clients connect to the service over WebSocket or XMPP-like persistent connections, using end-to-end encryption before any message leaves the device. A load balancer and API gateway route traffic to a pool of chat servers, which are often implemented in languages like Erlang or Elixir, because they excel at handling millions of lightweight concurrent connections. Each chat server manages active sessions, routes messages, and writes to a message queue. When a recipient is online, the message is pushed directly. When offline, the message is stored in a message store or queue and delivered later. A media storage service handles images, videos, and documents by encrypting them client-side and storing the encrypted blobs in an object store. A group service expands a single group message into multiple fanout deliveries, either by broadcasting to all members or by maintaining per-member message queues. A presence and last seen service tracks user activity and broadcasts updates to interested contacts. A push notification service wakes up mobile devices and displays alerts when the app is not active. Finally, a sync and multi-device service keeps message state consistent across all linked devices. The key metrics to memorize: cold. Daily active users in the billions for WhatsApp. Messages sent per day over 100 billion. Messages per second peak throughput, which is in the millions. End-to-end encrypted message percentage, ideally 100% for one-to-one chats. Media messages as a percentage of total messages, which is typically a large fraction. Median message delivery latency, measured in milliseconds for online users and seconds for offline delivery. Group size limit, currently thousands of members. Voice and video call completion rate, a strong measure of call quality. Push notification delivery latency, which matters for user experience. Storage costs per message and per media object, because media dominates cost. And system availability, usually measured in nines. These metrics are what interviewers and operators actually care about. Let's trace the end-to-end user journey. Alice opens WhatsApp and sends a text message to Bob. The app encrypts the message locally with Bob's public key, using the Signal protocol for end-to-end encryption. The encrypted message is sent over a WebSocket connection to a chat server. The chat server looks up Bob's active session. If Bob is online, the server routes the message to Bob's connected chat server in real time. If Bob is offline, the server writes the message to Bob's message queue or inbox in the message store. The message store returns an acknowledgement to Alice, who sees a single check mark. When Bob comes online, his chat server pulls pending messages from the store, decrypts them with his private key, and displays them. Bob reads the message, and a red receipt updates Alice's status to 2 blue check marks. If Alice sends a photo to a group of 500 members, the client encrypts the media for each member, uploads the encrypted blob to media storage, and sends a lightweight media reference to the group fanout service, which then delivers the reference to every group member's message queue. The core models and algorithms. The user model manages accounts, phone numbers, public keys, profile information, and privacy settings. The session model tracks active WebSocket connections, device identifiers, and routing state. The conversation model stores metadata about one-to-one and group chats, including participants and settings. The message model contains message identifiers, sender, recipient, encrypted payload, timestamps, and status such as sent, delivered, or read. The presence model tracks online, offline, and last seen state with publish-subscribe semantics. The group model manages group membership, admins, and message fanout. The media model stores encrypted media references, upload status, and expiration. The Signal protocol uses double ratchet algorithms to provide forward secrecy and future secrecy, meaning even if a key is compromised, past messages remain safe. The fanout algorithm for groups can use either write-time fanout, which writes a copy per member, or read-time fanout, which stores one copy and reads per member, depending on group size and read patterns. The sync model uses a conflict-free replicated data type or last write-win strategy to keep message state consistent across devices. Now the low-level design deep dive. The message store is typically a wide column or key value store keyed by recipient and message identifier, allowing efficient read of pending messages. The chat server layer is stateful for active sessions, but delegates persistence to the message store so that servers can be replaced. Media is stored as encrypted blobs in an object store, with a content delivery network for popular downloads, while the media metadata in the message points to the encrypted object. The push notification service sends a lightweight encrypted payload through Apple Push Notification Service or Firebase Cloud Messaging, without revealing message content. The group fanout service writes messages into per-member inboxes for large groups, which is simpler for reads but more expensive for writes, and may use a hybrid approach for smaller groups. The presence service uses a heartbeat or last activity timestamp with a time-to-live cache, and publishes changes to subscribed contacts. Multi-device sync stores an encrypted message history or device queue, so that each linked device can catch up on missed messages. The Signal Protocol key store runs on the client, while the server only relays pre-keys and public key bundles. Key takeaways for your interview. First, WhatsApp is fundamentally a distributed real-time routing and storage problem. Encrypt on the client, store and forward on the server, and deliver with low latency. Second, end-to-end encryption is the headline feature, so be ready to explain the Signal Protocol, pre-keys, forward secrecy, and why the server cannot read messages. Third, media handling is critical. Encrypt on the device, upload once, store in object storage, and use references to avoid duplicating large payloads in every message queue. Fourth, group chat fanout is a classic scale trade-off between write-time fanout, read-time fanout, and hybrid approaches based on group size and activity. Fifth, presence, last seen, message sync, and multi-device support are subtle but important design details that separate good answers from great answers. If you can walk through this system with these 5 points, you will signal strong senior-level design thinking. That's it for Design WhatsApp. If this helped, like and subscribe, and I'll see you in the next one at Cloud Wizard. And that's a wrap on Design WhatsApp. We covered the full picture, from end-to-end encryption and the Signal Protocol, through chat servers, message routing, media storage, group fanout, presence, and multi-device sync. If this video helped you, please hit that subscribe button and the bell icon so you never miss a new system design video. Drop your questions in the comments below. I read every single one. See you in the next one at Cloud Wizard.